What is matter? There are many possible definitions for matter in science. Matter, the term for any type of material. Matter is anything that has mass and take up space at a minimum. Matter requires at least one subatomic particle. So matter consists of atoms. The word matter is sometimes used to refer a pure substance. Examples of matter: proton, atoms, molecules, compounds, cat, tree, house, computer, example, etc. Examples that are not matter: photons, heat, light, thoughts, microwaves.
NutraBay.com is an authorized retailer for many high quality trusted brands like Optimum
Let me
Nutrition,
skip ad.
Ultimate Nutrition, MyProtein and Isopure. The protein powder which I ordered from NutraBay was delivered to me free of shipping cost in just 2 days. Since NutraBay is an authorized retailer, a certified website for these brands, you can buy protein powder from them without any worry. You have my word for it.
Physical and chemical properties of matter. Each phase of matter has its own chemical and physical properties. The phases of matter are solid. A solid has a definite shape and volume. Liquid. A liquid has a definite volume but can change shape. Gas. The shape and volume of a gas can change. These phases of matter can change from one to another. Melting. Melting occurs when a substance changes from a solid to a liquid. Boiling. Boiling is when a substance changes from a liquid to a gas. Condensing. Condensation is when a gas changes to a liquid. Freezing. Freezing is when a liquid changes to a solid. The changes that take place in substances may be categorized in two classes. Physical change, which does not produce a new substance, for example, phase changes, crushing a can. Chemical change, which produces a new substance, for example, burning, rusting, photosynthesis. Solutions. A solution results from combining two or more substances. Making a solution can produce either a physical or chemical change. The original substances can be separated from one another if the solution produces only a physical change. The original substances cannot be separated from one another if a chemical change took place. Thanks for watching. To learn more, visit about.com.
The concentration between matter and radiation. Connection. The dark energy.
Pay instantly with net banking on singaporeair.com.
My name's James Lincoln. I'm a physics teacher here for About.com. The Higgs boson is a well-described particle with a specific mass and behavior. It's named after Peter Higgs, a British physicist, although other people theorized its existence too. And it's the last particle member of the Standard Model of particle physics. A boson is a particle that gives forces to other particles, or it pushes and pulls on them. For example, the Higgs boson is supposed to pull on the W and Z bosons, which are also theoretical particles, but their existence is well supported by experiment. The Higgs particle is not like an electron, which you can get an electron stuck on a drop of oil and make specific measurements on it. The problem with the Higgs boson that makes it so difficult to detect is that it only lasts for 10 to the negative 22 seconds, too short to be measured in any reasonable way. Therefore, we have to measure its decay components, or the other particles that it will break up into after it radioactively decays. The Higgs boson is also supposed to be a neutral particle, very much like the photon, which is the particle that exchanges forces between electrons. In fact, the particle of light, the photon, is a good example of another neutral boson. Imagine two electrons traveling toward each other. They would be repelled because same charges repel. And the mediator that repels them is called the photon, or a particle of light. The photon is a boson. It does exactly what they're supposed to do. It repels or pushes away as a force. That's the idea, that forces are mediated by particles. I prefer the term mediator to either force or particle, because I feel that's exactly what we're talking about. Now, there are other bosons, such as the W and Z bosons. These are the ones that cause radioactivity. And the mechanism that they get their mass from, being massive bosons, is that the Higgs boson couples to them. It's a coupler that gives other particles their mass. That's the whole idea with the Higgs boson. The Higgs mechanism is the first time we have a theoretical model that seems to work of a particle that gives mass to other particles. I'm James Lincoln for About.com. Thanks for watching.
Pure substances definition. Examples of pure substances are water, diamond, gold, sodium chloride, ethanol, brass, bronze, saline solution. Examples that are not pure: rock, orange, wheat, light bulb, shoe, sandwich, etc. Common definition of a pure substance. Which definition do we use? It does not matter which definition we use, but if you are asked to give examples of pure substances as a homework assignment, go with examples that meet the narrow definition: gold, silver, water, salt, etc. What are some examples of matter? Examples of matter around us are many. See.
Pay instantly with net banking on singaporeair.com.
Hi, I'm Emerald Robinson, and in this What Is video, we're going to investigate the state of matter called a solid. Solids are materials that keep their form. That is, solids don't change their shape or expand to fit the container that they are in. Although there are many different solids, there are a few characteristics that they have in common. First, the particles in a solid are arranged so that they remain close to one another. But this does not mean that there is no movement at all. Electrons still orbit the atom's nucleuses, and the atoms themselves vibrate or jiggle, but the molecules in a solid always stay in close proximity. Second, solids can't be compressed. Because there's not a lot of space between the atoms, they can't be squeezed together any closer than they already are. Sometimes scientists say that solids are a condensed phase of matter. Third, in general, solids have melting and boiling points that are higher than room temperature. Solids are sometimes classified by how their atoms are arranged. If the atoms in a substance are in a pattern, the solid is known as a crystal. Common crystals are ceramics and diamonds, which are large single crystals. If the atoms in a substance are not arranged in a pattern, the solid is called amorphous, which means without a form. Common amorphic solids include plastics and glass. Most of the time, solids are not made of all of one kind of atom, or even made consistently of the same material. These types of solids are called mixtures, or more scientifically, composites. Most of the things we see every day are composites, especially things in nature like rocks, wood, and soil.
Things that are not matter: time, sound, sunlight, rainbow, love, thoughts, gravity, microwaves, heat, memories, information, reflection, energy. Other example includes dreams, magnetism, radio, and heat. Here is why. Here is the answer for why light and heat not matter. In science, you might have learned that everything is made up of matter. However, you can see and feel things that aren't matter. For example, light and heat are not matter.
For example,
Here's an explanation of why this is and how you can tell matter and energy apart. Key takeaways. Matter has mass and occupies space. Heat, light, and other forms of electromagnetic energy do not have measurable mass and can't be contained in a volume. Matter can be converted into energy and vice versa. In many cases, matter and energy are found together. An example is fire. Here is the reason for the main question. Energy, sunlight, sound, gamma radiation, energy contained in chemical bonds, electricity, hydrogen gas, a rock, alpha particle. Many of them are. state of matter definition. How to define a gas in a chemistry way. Gas is defined as a state of matter consisting of particles that have neither a defined volume or definite shape. It's one of the four fundamental states of matter along with solids, liquids, and plasmas under ordinary conditions. The gas state is between the liquid and plasma states. Gas may consist of atoms or element, example H2Al, H2, or compounds, example HCl, CO2, or mixtures, example air, natural gas. Here are the examples of gas. Properties of gases.
Whey protein is a milk-based protein supplement safe for both men and women. NutraBay.com is an authorized retailer for many high-quality, trusted brands like Optimum Nutrition.
Hi, I'm Emerald Robinson, and in this What Is video, we're going to investigate the state of matter called a gas. Gases are materials that have no definite volume and no specific shape. In other words, gases can easily flow into and take the shape of a container and will expand, redistributing themselves to evenly fill that container. Although there are many types of gases, there are a few characteristics that they have in common. First, particles in a gas have no real arrangement. They can move over and past one another, and the space between the molecules can increase or decrease. Molecules in a gas collide with one another and move more quickly or more slowly based on factors like temperature and pressure, but they will always spread out fairly equally to fill the space that they're in. All of this molecular movement means that gases hold a lot of kinetic energy caused by motion. Second, gases can be compressed. Because there is space between the molecules in a gas, it can be placed under pressure and squeezed so that the particles are forced to be close to one another. Third, gases can flow from one area to another, although the direction of flow is not directly affected by gravity. This ability to flow means they are sometimes referred to as fluids. Last, gases have melting points and boiling points that are below room temperature. For the most part, we are unable to see gases because of the space between their particles. Scientists have to use characteristics like pressure, volume, number of particles per unit area, and temperature to discuss and identify them. Gases are commonly used in things like cooking, healthcare, and scientific research, and they even make up the air we breathe.
Okay, let's see all the states of matter. All states of matter, let it be in the earth or universe. Let us see and learn.
I think we're all reasonably familiar with the three states of matter in our everyday world. They're at very high temperatures, you get a fourth. But the three ones that we normally deal with are things could be a solid, a liquid, do that in blue, well, it doesn't have to be blue, or it could be a gas. And we have this general notion, and I think water is the example that always comes to, at least my mind, is that solid happens when things are colder, relatively colder. And then as you warm up, you go into a liquid state. And as you warm up even more, you go into a gaseous state. So you go from colder to hotter. In the case of water, when you're a solid, when you're solid, you're ice. When you're a liquid, some people would call ice water, but let's call it liquid water. Liquid water, I think we know what that is, liquid water. And then when it's in the gas state, you are vapor or steam. Vapor or steam. So let's think a little bit about what at least in the case of water, and the analogy will extend to other types of molecules, but what is it about water that makes it solid and when it's colder, what allows it to be a liquid? And I'll be frank, some liquids are kind of fascinating because, you can never you can never nail them down, I guess is the best way to view them, or a gas. So let's just draw a water molecule. So you have oxygen there, you have some bonds to hydrogen, and then you have two extra pairs of valence electrons in the oxygen. And we did a couple of videos ago, we said, hey, oxygen is a lot more electronegative than the hydrogen, in that it likes to hog the electrons. So even though this shows that they're sharing electrons here and here, right, at both sides of those lines, you can kind of view that, hydrogen's contributing electron and oxygen's contributing electron on both sides of that line. But we know, because of the electronegativity or the relative electronegativity of oxygen, that it's hogging these electrons. And so the electrons spend a lot more time around the oxygen than they do around the hydrogen. And what that results is that on the oxygen side of the molecule, you end up with a partial negative charge. We talked about that a little bit. On the hydrogen side of the molecules, you end up with a slightly positive charge.
State of matter.
Positive. Now, if you have very little, if these molecules have very little kinetic energy, they're not moving around a whole lot. But the positive sides of the hydrogens are very attracted to the negative sides of oxygen in other molecules. Let me draw some more molecules. So when we talk about the whole state of the whole matter, we actually think about how the molecules are interacting with each other, not just how the atoms are interacting with each other within a molecule. So let's say that I just drew one oxygen. Let me copy and paste that. But I could do multiple oxygens. And let's say that hydrogen is going to want to be near this oxygen because this has partial negative charge, this has a partial positive charge. And then I could do another one right there. And then maybe we'll have, and just to kind of make the point clear, you have two hydrogens here, maybe an oxygen wants to hang out there. I'll do it so maybe you have an oxygen that wants to be here because it's got its partial negative here and it's connected to two hydrogens right there that have their partial positive. But you can kind of see a lattice structure being, let me draw these bonds, these polar bonds that start forming between the particles. These bonds, they're called polar bonds because the molecules themselves are polar. As you can see, it forms this lattice structure. And if each of these molecules don't have a lot of kinetic energy, or if we say the average kinetic energy of this matter is fairly low, and what do we know is average kinetic energy? Well, that's temperature. Then this lattice structure will be solid. Solid. These molecules will not move relative to each other. They're all, I could draw a gazillion more, but I think you get the point that we're forming this kind of this fixed structure. And while we're in the solid state, as we add kinetic energy, as we add heat, what it does to the molecules is it just makes them vibrate around a little bit. So the kinetic energy just makes these, if I was a cartoonist, the way you'd draw like a vibration is put little quotation marks there. That's not very scientific. But they would vibrate around. They would buzz around a little bit, drawing arrows to show that they're vibrating. It doesn't have to be just left, right. It could be up, down. But as you add more and more heat in a solid, these molecules are going to keep their structure. So they're not going to move around relative to each other, but they will convert that heat, and heat is just a form of energy, into kinetic energy, which is expressed in these as the vibration of these molecules. Now, if you make these molecules start to vibrate enough, and if you put enough kinetic energy into these molecules, what do you think is going to happen? Well, this guy is vibrating pretty hard, and he's vibrating harder and harder as you add more and more heat. This guy is doing the same thing. At some point, these polar bonds that they have to each other are going to start not being strong enough to contain the vibrations, right? And once that happens, the molecules, let me draw a couple more. Once that happens, the molecules are going to start moving past each other, right? They'll start moving past each other. So now all of a sudden, the molecule will start shifting. But they're still attracted to, maybe this side is moving here, that's moving there, you have other molecules moving around that way, but they're still attracted to each other, right? Even though we've gotten to the kinetic energy to the point that the vibrations can kind of break the bonds, can break the bonds between the polar sides of the molecules, it's still, our vibration or our kinetic energy for each molecule still isn't strong enough to completely separate them. They're starting to slide past each other. And this is essentially what happens when you're in a liquid state, is that you have a lot of atoms that are just, they want to be touching each other, but they're sliding. They have enough kinetic energy to slide past each other and break that solid lattice structure here. And then if you add even more kinetic energy, even more heat to the at this point, it's a solution now. You're going to break. They're not even going to be able to stay together. They're not even going to be able to stay near each other. If you add enough kinetic energy, they're going to start looking like this. They're going to completely separate and then kind of bounce around independently. Especially independently if they're an ideal gas, but in general, a gas is they're no longer touching each other. They maybe they might bump into each other, but they have so much kinetic energy on their own that they're all doing their own thing and they're not touching. And I think that makes kind of intuitive sense if you just think about what a gas. You for example, it's hard to see a gas. Why is it hard to see a gas? Because the molecules are much further apart, so they're not acting on the light in the way that a liquid or a solid would. And if we keep making that extension further, a solid. Well, I probably shouldn't use the example with ice because ice or water is one of the few situations where the solid is less dense than the liquid. That's why ice floats, and that's why icebergs don't just all fall to the bottom of the ocean, and ponds don't completely freeze solid. But you can imagine that because a liquid is, in most cases, other than water, less dense, that's another reason why you can see through it a little bit better, or it's not diffracting. Well, I won't go into that too much, than maybe even a solid. But the gas is the most obvious, and it is true with water. The liquid form is definitely more dense than the gas form, that the gas form will kind of, the molecules are just going to jump around, not touch each other, and because of that, more light can kind of get through the substance. Now, the question is, how do we measure the amount of heat that it takes? The amount of heat that it takes to do this to water? And to explain that, I'll actually draw a phase change diagram, which is a fancy way of describing something fairly straightforward. So let me say that this is the amount of heat I'm adding, and this is the temperature. And then we'll talk about the states of matter in a second. So heat is often denoted by Q. Sometimes people will talk change in heat. They'll use H, lowercase, uppercase H. They'll put a delta in front of the H. Delta just means change in. And sometimes you'll hear the word enthalpy. Let me write that because it was a word that I used to. I'd say, what is enthalpy? It sounds like they're using an enthalpy. It sounds like empathy, but it's quite a different concept, at least as far as my neural connections can make it. But enthalpy is it is closely related to heat. It's heat content. It's heat content. Heat content. For our purposes, when you hear someone say change in enthalpy, you should really just be thinking of change in heat. I think this word was really just introduced to confuse chemistry students and introduce a non-intuitive word into their vocabulary. The best way to think about it is heat content. Change in enthalpy is really just change in heat. And just remember, all of these things, whether we're talking about heat, kinetic energy, potential energy, enthalpy, you'll hear them in different contexts. You're like, oh, I thought I should be using heat, and they're talking about enthalpy. Or these are all forms of energy. And these are all measured in joules. And they might be measured in other ways, but the traditional way is joules. And energy is the ability to do work. And what's the unit for work? Well, it's joules, force times distance. But anyway, that's a side note. But it's good to know this word enthalpy, especially in a chemistry context, because it's used all the time. And it can be very confusing and non-intuitive, because you're like, where did this enthalpy? I don't know what enthalpy is in my everyday life. Let's just think of it as heat content, because that's really what it is. But anyway, on this axis, I have temperature, I have heat, right? So this is when I have very little heat, and I'm increasing my heat. And this, say, is temperature. Temperature. Now, let's say at low temperatures, I'm here, and as I add heat, my temperature will go up, right? Temperature is average kinetic energy. Let's say I'm in the solid state here, and I'll do the solid state in purple. And so as I add heat, I already was using purple. I'll use magenta. So as I add heat, my temperature will go up, right? Heat is a form of energy, and when I add it to these molecules, as I did in this example, what did it do? It made them vibrate more, or it made them have higher kinetic energy, or higher average kinetic energy, and that's what temperature is a measure of, average kinetic energy. So as I add heat in the solid phase, my average kinetic energy will go up, and let me write this down. This is in the solid phase, solid, or the solid state of matter. Now something very interesting happens. Let's say this is water. Let's say this is water. So what happens at this is 0 degrees. I'll do 0 degrees, which is also 273.15 Kelvin, 0 degrees Celsius. But let's say that's that line. What happens to a solid? Well, it turns into a liquid. Ice melts. I mean, not all solids. We're talking in particular about water, about H2O. So this is ice in our example. All solids aren't ice. Although you could think of a rock as solid magma, because that's what it is, right? You can think of I could take that analogy a bunch of different ways. But an interesting thing that happens is, at 100 degrees, or at 0 degrees, right? Depending on what direction you're going, either the freezing point of water or the melting point of ice, something interesting happens. As I add more heat, the temperature does not go up. As I add more heat, the temperature does not go up for a little period. Let me draw that. For a little period, the temperature stays constant. So, and then, while the temperature is constant, it stays a solid. we're still a solid. And then we finally turn into a liquid. Let's say right there. So we added a certain amount of heat and just stayed a solid, but it got us to the point that the ice turned into a liquid. It was kind of melting the entire time. That's the best way to think about it. And then, once we keep adding more and more heat, then the liquid warms up too. So then the liquid warms up. Now, we get to what temperature becomes interesting again for water. Well, obviously, 100 degrees Celsius, or 373, let me draw it like this, or 373 degrees Kelvin. I'll do it in Celsius because that's what we're familiar with. What happens? That's the heat, that's the temperature at which water will vaporize, or which water will boil. But something happens, and why is it? They're really getting energy, kinetically active. But just like when you went from solid to liquid, there's a certain amount of energy that you have to contribute to the system, and actually it's a good amount at this point, where the water is turning into vapor, but it's not getting any hotter. So it's turning into vapor, but it's not getting any hotter. So we had to keep adding heat, but notice the temperature didn't go up, and we're going to talk about in a second what was happening then. And then finally, after that point, where we're completely vaporized, or we're completely steam, then we can start getting hot. The steam can then get hotter as we add more and more heat to the system. So the interesting question is, I think it's intuitive that as you add heat here, we're going to get, our temperature is going to go up. But the interesting thing is what was going on here. We were adding heat. So over here, we're turning our heat into kinetic energy. Temperature is average kinetic energy. But over here, what was our heat doing? Well, our heat was not adding kinetic energy to the system. The temperature was not increasing, but the ice was going from ice to water. So what was happening at that state is that the kinetic energy, the heat, was being used to essentially break these bonds. And essentially bring the molecules into a higher energy state. So you're saying, Sal, what does that mean, higher energy state? Well, if there wasn't all of this heat and all of this kinetic energy, these molecules want to be very close to each other, right? For example, I want to be close to the surface of the Earth. When you put me in a plane, you have put me in a higher energy state. I have a lot more potential energy. I have the potential to fall towards the Earth. Likewise, when you move these molecules apart and you go from a solid to a liquid, they want to fall towards each other. But because they have so much kinetic energy, they never quite are able to do it. But their energy goes up. Their potential energy is higher because they want to fall towards each other. By falling towards each other, in theory, they could do some work. So what's happening here is when we're contributing heat, and this amount of heat we're contributing, it's we could either call it, when you're going in, it's called the heat of fusion. Because it's the same amount of heat regardless of how much direction we go in. When we go from solid to liquid, it's we can view it as the heat of melting, right? It's the heat that you need to put in to melt the ice into liquid. When you're going in this direction, it's the heat you have to take out of the 0 degree water to turn it into ice. So it's the heat that you're taking that potential energy and you're bringing the molecules closer and closer to each other. So the way to think about it is, right here, this heat is being converted to kinetic energy. Then, when we're at this phase change from solid to liquid, the heat is being used to add potential energy into the system, to pull the molecules apart, to give them more potential energy. If you pull me apart from the Earth, you're giving me potential energy because gravity wants to pull me back to the Earth, and I could do work when I'm falling back to the Earth. A waterfall does work. It can move a turbine. You could have a bunch of falling Sals move a turbine as well. And then, once you are fully liquid, then you just become a warmer and warmer liquid. Now the heat is once again being used for kinetic energy. Right? You're making the water molecules move past each other faster and faster and faster to some point where they want to just completely disassociate from each other. They want to not even slide past each other, just completely jump away from each other. And that's right here. This is the heat of vaporization. So this is the heat of vaporization. Heat of vaporization. And that the same idea is happening. Before we were sliding next to each other. Now we're pulling them apart all together. So they could definitely fall closer together. And then once we've added this much heat, now we're just heating up the steam. We're just heating up the gaseous water, and it's just getting hotter and hotter and hotter. But the interesting thing there, and at least the interesting thing to me when I first learned this, is that there are these states that you can have. Whenever I think of 0 degrees water, I always say, oh, it must be ice. But that's not necessarily the case. If you start with water and you make it colder and colder and colder to 0 degrees, you're essentially taking heat out of the water. You can have 0 degree water, and it hasn't turned into ice yet. And likewise, you can have 100 degree water that hasn't turned into steam yet. You have to add more energy. You can also have 100 degree steam. You can also have a 0 degree water. Anyway, hopefully that gives you a little bit of intuition of what the different states of matter are. And in the next problem, we'll talk about how much heat exactly it does take to move along this line, and maybe we can solve some problems on how much ice we might need to make our drink cool.